Hello everybody and welcome back. This is part 2 of the series I've done on the question, what is electricity? In the last part, which I would highly recommend you watch before this part because it sets some basic groundwork that we'll need here, I talked about basically the basics of what electricity is. And I focused in that one entirely on so-called direct current, which I described as chemically generated electricity, the electricity that comes out of something like a battery, where the current will flow out the battery, out the positive, through, say, a lamp to turn the lamp on, and back the negative, back to the battery. Quick aside, that's conventional current. Conventional current flows from positive to negative. The actual electron flow is negative to positive, but that's a distinction that is more advanced. For the purposes of most basic theory stuff, current flows from positive to negative. In this video, I'm going to be talking more about what I described as mechanical generated electricity, which is alternating current. That is the electricity that would come out the sockets on the wall, for example. Electricity, alternating current electricity, is not used very much by most things. The majority of the devices in your home, the first thing they'll do is convert the AC into DC to use for whatever. The only things that don't need to do that are basically resistors, so heating elements and like incandescent light bulbs. Other than that, pretty much everything. Oh, electric motors is another one. But other than that, other than like heating elements, incandescent light bulbs and electric motors, pretty much everything, the first thing it does is turns the AC into DC. So you might ask then, why do we use AC if the first thing that pretty much everything does is turn the AC into DC, and all of the things that rely on AC could also use DC? Why do we send AC through the wall? Why don't we just send DC? Because it would save us a step. And there's a fairly simple explanation for that, which I will get onto in a minute. But first, I would like to talk about the difference between AC and DC, the fundamental difference, which is what makes it so annoyingly difficult to work with. I have here these leads, which are connected to a device called an oscilloscope, which is basically a voltmeter, a very, very accurate voltmeter, which also has a very accurate clock built into it. And what it does is it measures the AC, it measures the voltage between these two probes, and it will then save that, and every set period of time it will take another measurement, and it then makes us a graph of the output, whatever the waveform of the voltage between these probes is on the screen. I'm recording the screen, and I will put it in the corner so you can see it, and I will then be able to do that to show you the difference rather than just describing it. Here are some leads coming from my power supply, which I will connect to the ones on the oscilloscope, and you will see on the scope screen we have a straight line. That is DC, direct current. It flows directly in a straight line. You can tell that by the symbol for DC, which is a dotted line and solid line. It's a line. The voltage doesn't change over time, it's constant. That means it's very easy. Everything's constant over time, nothing changes. So if you have a set resistance, the current is always the same too, because the voltage never changes, for example. With AC, that's not how it is. I have, over here, which I will bring in, an AC supply. What these components are is not important, I'll get into that later, but basically what they're doing is they're taking the mains AC from the grid, because that's the easiest source of AC power I have, and they're making it safe so that I can touch the output and not get shocked. I will then attach this to the scope as I was doing before, and you will see on the screen the key difference. Before we had a straight line, and now we have a sine wave, which is where the voltage goes up and down, and key, it goes, the line on the scope you'll see, I should move my hand so you can see them, not behind where the scope's going to be, but the line on the scope is 0 that goes across, and you can see the voltage is both above and below 0. It goes both ways. That's where the name alternating current goes. It alternates direction. In this case, because I'm in Europe, it alternates direction 50 times per second. It's 50 hertz, which is the frequency. In America, that would be 60 hertz, 60 times per second. That is the bit that makes this annoying. Because it's flipping direction so often, it means that it will behave in unexpected ways, which I shall go on to explain now. I'm going to do my best to simplify this, but a lot of it's really complicated, so I'm sorry in advance. I hate AC theory, it's just annoying. So, paper and pen, and let's explain this. The big drawback with DC, and I know there's a lot of people who are about to go, I'm actually going to get in the comments and start typing angry things. Let me explain, because you are wrong. You cannot change the voltage of DC up. It is impossible. Now, all those people I talked about who are going, actually, are going to be talking about buck boost converters. Buck boost converters do indeed take a DC voltage and they step it up to a higher DC voltage, or they step it down to a lower one. However, they do not actually change a DC voltage. What they do is they take the DC voltage, they use some complicated electronics to then break the DC back and turn it into AC. They then change the voltage as AC and then do a thing called rectification to turn it back into DC again. And once they've turned it back to DC, they then output it. So it looks like you feed DC in, you get DC out, but you don't. Actually, what happens is you feed in your DC waveform like this, and then inside the machine, or inside the module, it will be chopped into a square wave like this. Usually it's a square wave, they don't use sine wave inverters for this kind of thing. Into a square wave. That then gets transformed into a lower voltage like this, or into a much higher voltage like this, and then they turn that into a DC output again, but a much higher one, or a lower one, depending on what you're doing with the power supply. You cannot change a DC voltage up or down, and this is a huge problem for grid scale distribution, which is what the power that comes out of your wall is. The power that comes out of your wall is not generated locally, usually. The power that comes out of your wall could be generated hundreds or even thousands of miles away, and is then sent through big long cables to get to your house. And I'll draw you a diagram of this to explain it, because it's a bit hard to get your head around. We have your house here. Crude drawing of a house. This is you, where you live. You plug your kettle in or whatever, or you turn your light on. The power has to come from somewhere. There are cables then that run through your street, like this, and all of your neighbours' houses will also be connected onto the same cable. At the end of your street, or depending where you live, there'll be somewhere fairly close by to you. My one is literally just across the street out my window. There will be somewhere a thing known as a substation, which is basically a place where they change the voltage. So there's a thing called a substation, which is basically a big box like this. I'll explain in more detail again how these work, but it has a component in it known as a transformer, because it transforms voltages. And the way the transformer works, it will have two or more windings depending on how it's set up. One of them is called the primary, and you apply power to the primary winding, and the secondary winding will then output a different voltage. So in this case, for me, where I am in Europe, the secondary winding here, so this is one coil of wire, the secondary winding will output 230 volts / 400 volts. I will then explain why there's two voltages here. Again, AC is weird, I did warn you about this. On the other side, there is a winding here, which is 6.6 kV / 11 kV, which is 6,600 or 11,000 volts. Again, I'll explain why two voltages in a minute. Those wires then run, there'll be wires that run back to another even bigger substation. This one will be further away, where there's another transformer, and the secondary of that transformer outputs the 11,000 volts. The primary on this transformer is fed with 33,000 volts. So you then have your 33 kV distribution. I can't remember the phase to ground voltage for 33 kV. Yeah, it doesn't matter, but 33 kV. Because I should say, for people who are going, distribution doesn't use phase to ground much. They mostly use phase to phase because transformers, the way they're wired, again, I will explain this in a minute. If you don't understand it, don't panic. They use 33 kV. That is then fed from another substation, which will take voltage, usually 132,000, 275,000 or 400,000, depending on how big of an area you live in. For me, my 33 is fed from a 275 station, which is just outside of the town I live in, which is not normal. Usually it's further away than that, but I happen to live near a rather large power station. So there is then it'll be like 132 or 275 or 400, depending on the area you're in, kV. And on the end of this big line here is where the actual big factory with the generators in is, where that will then generate the power which is sent. So this here could be hundreds or thousands of miles away, and it travels through all of this to power your home. And again, one of the ways the grid works is it is a grid. I will put a link in the description to a very interesting map, actually, of the continuous European power grid, which is a massive interconnected electricity grid which covers everywhere from like northern Africa right across to Turkey, and I think it even goes into Saudi Arabia, and right up to like the UK and the Norway. It covers a huge area, all interconnected with these big huge pylons with high voltage power. And the idea is that wherever power is needed, we can get it there. Because we'll have somewhere, there always will be a generator which is not at full capacity, and somewhere there will be a load. So we can always get more power wherever it's needed through all of these interconnected cables. But this is the basic setup. Usually there'll be spurs off all over the place where things like this 400 kV line will probably feed loads and loads of 33 kV stations, which will each feed loads and loads of 11 kV stations, and they're not wired like this. They're usually wired in discontinuous rings, which again is a technicality. Basically what that means is you have your substations are these boxes like this, and then you'll have a big substation here and a big substation here. So let's say these are 33 kV substations, and each of these ones here are 11 kV. What would happen is the wire will come out of this substation, it will go to here, and then it will loop like this. And then there'll be one coming from here, and it will loop like this. And then at some point in between these two substations, there will be a cable that comes out of that substation and one that comes out of that substation, and there will be a switch here, which is normally open. It's called a normally open point. And under normal circumstances, these two are completely independent. But let's say something goes wrong. Let's say there's maintenance that needs to be done, or something blows up or goes on fire or whatever. They can close this switch here and then say we need to do some maintenance on this substation. We can get rid of it and disconnect it, and this substation can feed through here, through the switch, and keep all of the power on. Which is why power outages are not very common, because the grid being designed as it is, they can almost always keep the supply on to almost everybody, even when they have to turn things off to do maintenance on them. But that's a side point. The distribution like this relies, as you can see, on these voltage transformers. The reason for that is because when you have a resistance, a cable has a resistance. I talked about this last time. That resistance is usually low, but when you're talking cables on this kind of scale where they're crossing oceans or running the entire length of countries, it could be 100 or 1,000 miles long, that resistance starts to add up a lot. And the more current you pull through a cable, the more volt drop you will get across a cable. Again, I'll do another video talking about this kind of calculation work later, but just trust me for now. That volt drop becomes very problematic. If your cable is too long and you lose too much volt drop, A, it's very, very inefficient because you're wasting a lot of power in the cables, and B, the voltage you get out the other end isn't usable. The way it used to work back in like the early 1900s is you'd have one big power station and it would directly feed a voltage to a few customers in the immediate vicinity. So they used all sorts of voltages back then: 75 volt DC, 110 volt, 90 volt, 240 volt. There were countless different standards all competing. And they used low voltages distributed directly to the customers. That's fine, but you can only do that over a certain distance. I said the volt drop begins to become problematic. So somebody decided, I know, why don't we step the voltage up, make it much higher, and then if we drop, say we're going to go across a cable, if we are dropping 100 volt across a cable run, if it was 240 volt, we've dropped almost half the voltage. But if we make that voltage, say, 33,000 volt, 100 volt of volt drop, that's nothing. That we can ignore that. So when we then step it down, it's more efficient. That is the key that allows the grid to function. Because if you had the way it used to work, you'd have a local power station supplying a few local people. It's very unreliable. If something goes wrong, there's no way to backfeed like I was showing here. There's no interconnection. And you have to have power stations everywhere. Whereas nowadays, we can have a huge power station, like say Drax in England, I think is 6 gigawatt. That's 6 billion watts of power. That's an enormous amount of power. That would be like enough power to run almost the entire country of Ireland pretty much by itself. So we can have these huge power stations and then just send the power wherever it's needed. This is only possible with AC, as I said, because you have to turn DC back into AC in order to transform it and then rectify it again. So we can't send DC long distances. Again, there are going to be people in the comments, actually, yeah, the high voltage long distance DC power transmission does exist because it's more efficient, and I will then explain why, because there's weirdness that goes on. But that's only been possible very recently. That's only been possible in like the past few decades. Probably not even the past few, like the past decade. We had the technology in order to make AC and DC swap them back and forth so easily and efficiently enough that it was actually worthwhile. So a lot of the big interconnecting power lines now that run from, say, Norway to the UK, there's one, that's DC. Or they're building one that goes from the Highlands to Shetland. That's DC, because the parasitic losses are higher. Let's now explain parasitic losses. Actually, no, let's not do that, that's complicated. I should explain how AC is generated first. Sorry, I'm going all over the place. I don't script these. I probably should. Yeah. So I said AC is mechanically generated. It's generated by spinning a generator. And if we have a generator here, the way it works is you have a magnet inside the generator like this, which we spin round, and every wire that has current flowing through it makes a magnetic field, and every magnetic field that passes through a wire makes an electrical current. So by spinning this magnet round and round and round, we can make an electrical current. And the way they do that, they have coils of wire, usually 3 of them. I'll explain that in a second. Here, like this. So as the magnet spins round, the voltage induced in that wire will go like this. It'll go up, and then as the magnet passes, it'll go back down again. And then as the other pole of the magnet comes, it will go up and back down again the other way. And doesn't that look a bit familiar to what I just showed you on the scope? So this is how it works. We get a waveform like this that's easy to generate, it's easy to change the voltages to send it long distances, and it's easy to use directly for things like old incandescent light bulbs, which is all they were using it for back when this system was built. I am pretty confident, to be honest, if we were building a new power grid from scratch today, I would almost guarantee it would be DC based, just because we use DC for pretty much everything nowadays, and we now have the technology to do this, so it's not a problem. But back before we had this technology, AC was the way to go. These, I said there was 3 coils, and some of you might be thinking, well, that's because there are 3 wires in a mains cable, there's 3 pins on my plug, but that's not how it works. The 3 pins on your plug is a line, a neutral, and an earth. Those go by different names depending on where in the world you are, but I'm going to call them that because that's what we call them in the UK. These 3 windings here produce 3 phases. 3-phase power is not used domestically much. It's mostly reserved for industrial purposes. But the way it works is the 3 windings each will produce a waveform like this, but it will be out of phase, so you'll end up with a waveform like this, and then you'll have another one like that. So you end up then with 3 peaks, like 3 waveforms, all the same, just shifted. Each of these phases, if we go between 2 phases, so we'll take here, we'll have neutral, L1, L2 and L3, which is neutral phase 1, 2, 3. If you go between any of these 2 phases, you'll get 400 volt in the UK, or Europe, you'll get 400 volt. But if you say go between any of these phases in neutral, you'll get 230. And that's what I meant up here when I said there was 2 voltages, and I'd explain why in a second. The smaller one is what's called phase to earth voltage, which is the voltage between the line conductor and the earth. The higher voltage is the phase-to-phase voltage, which is the voltage between the 2 live conductors. So on 11 kV, it's 11,000 volts between the 2 phases, only 6,600 volt between the phase and the earth. You have 3 phases, that's kind of the accepted standard now, but that's not the limit. You can have as many as you want, really, within reason. There is no theoretical limit on it, as far as I'm aware, but there's practical limits. The way that it works is you have, say on 3-phase, it's 120 degrees phase shift, because 360 degrees of rotation divided by 3 phases equals 120 degrees. If you wanted, you can have 2-phase, which is 2 phases 180 degrees out of phase. Sometimes 2-phase power is 90 degrees phase shifted, which is kind of 4-phase, but just missing 2 of them. Again, this is weird technicalities. 2-phase is strange. But you also get, say, 6-phase and 12-phase. You can go right up to like 64-phase or 170-phase if you wanted it. There's no limit. The reason we don't use more than 3 is because it's just not needed. It's additional. Every additional phase you run is another wire you have to pay for. So it's cheaper to run 3-phase than it is to run, say, 6-phase. And the power delivery trade-offs and stuff, it's not worth the additional cost. Sometimes you use more phases for other reasons. Like, for example, if you live in the south of England, they use, for powering their electric trains, a thing called third rail, which is 750 volts DC. That is generated from the national grid. So they take the incoming AC, use a transformer to change the voltage, and then rectify that into DC. They rectify it and then they can't smooth it though, because again, I'll get into this in future videos, but there's a thing called inrush current, and when the train starts up, it draws so much power they couldn't smooth that out. So what they do is they take the 3 phases, and using the black magic of transformers, they make it into 12 phases, and then rectify that, which gets you a much smoother output even under extreme loads. I will talk now about rectification. I'll get onto the parasitic load stuff that I was talking about before in a bit, but this section is getting very long, so I'm going to cut. I'll do a demonstration about rectification, and then we'll come back and talk about the parasitic stuff, because that's complicated. So, 1 second. So, the scope will be back in the corner again. Let me move this so you can see. What I've done is I've added this component here is a capacitor. I'll explain what that's for in a second. And this one here is the diode I was talking about. This is a half-wave rectifier. So what this will do is it will rectify half of the waveform. I will bring the scope back in and I'll show you what that looks like quickly. I will connect the ground here and the waveform there. And you can see the waveform on the scope. When I connect the capacitor to it, the capacitor is like a battery that will store energy. So when I connect it, you can see what happens. We have now a nice smooth DC. This is the simplest way to do rectification, but it's also the worst. Because when you only are charging in half the waveform, it means A, you're wasting half of the power because you're cutting it off. And also you're only charging it on the positive peak, so your discharge curve, if you put a load onto it, the voltage will dip much lower, rather than if you do a full bridge rectifier. So I will now cut, and I will show you what a full bridge rectifier would look like on this setup here. 1 second. So now you will see I have 4 diodes. The capacitor is out of circuit at the moment. I will bring the clips back in, and I will connect them up now. So we have... that is the negative and that's the positive. And you can see we have our lovely full wave rectified. So both halves of the waveform, the negative and the positive, are now positive peaks on the wave. If I put this capacitor back, where does it go? Goes in there, and then I put this back on again, you'll see we now have a lovely smooth DC. And now that's being charged off both halves of the waveform, so the positive and the negative half of the waveform, like both of them are now up the top. Both of them are charged to the capacitor, so the capacitor is charged twice as often, makes the output much smoother. You can imagine then how if instead of having one waveform charging the capacitor, we had 3, that would make the capacitor charged even more often. And let's say we had 6 or 12 like you do with the trains, that charged capacitor even more often, so the output you get is a much more stable voltage the more often you charge the capacitor. That's rectification in a nutshell. So, I just showed you rectification. Inverting is much more complicated than I'm not going to demonstrate that. Basically, the easiest way to think about it is just like a switch. You turn it on and off lots really, really fast, and it makes kind of an AC waveform, but it's more complicated than that. Anyway, one of the other things I want to talk about is, you'll remember that I said we use DC for certain transmission lines nowadays, now that we can. And the reason we do that is because AC has a few weird things that it likes to do which are very, very annoying from a power transmission point of view. The main ones are that AC is affected by impedance, not resistance. And I will explain what that means. Impedance is basically a combination of DC resistance, which is like the ohms measurements I was making in part 1, as well as what's called capacitive reactance and inductive reactance. That is getting quite complicated. I'm not going to really explain it in full, but in very simple terms, what it is that component I was using to smooth the DC is called a capacitor. They basically are used to store energy. But the other thing they can be done with is they can be used as a current limiting source on AC. Again, I'll do a full video about capacitors and what they are and how they work, but the most simple way to explain a capacitor is just two bits of conductive stuff separated by a bit of not conductive stuff. So that one I was using on the demonstration there, this one here, this has a bit of like paper basically inside it, which has metal foil on both sides of it. There are many, many different types of capacitors you get with all kinds of different things with different stuff sandwiched between them. But a capacitor, the symbol for it is this, and this is a good way to remember it. A capacitor, the symbol for a capacitor is two blocks like that. And you can imagine if we have an AC waveform like this, the AC waveform will pass between the capacitors, whereas a DC one would be blocked. So you can remember that capacitors pass AC because AC can fit through the gap in the capacitor. That's not how it actually works. It works because capacitor charges and discharges with the cycles of the AC. But anyway, AC will leak through a capacitor. It will see a capacitor as a resistance. That resistance is called the capacitive reactance. That has problems because, as I said, a capacitor is just two conductive things separated by a less conductive thing. And if you imagine when you look up and you see the big power pylons that they build, they have the arms on them like this, and they have usually 6 wires on each one. We have a conductive thing and another conductive thing and some not conductive air in between them. That is a capacitor. We have conductive things and the conductive earth the pylon is built on with, again, air between them. That causes more leakage. The pylon is earth. That causes leakage. So all of these capacitances, over short distances, they don't matter. Over much longer distances, they become really quite significant. And they can cause a fairly substantial amount of losses because current will leak through those. They're called parasitic capacitances. Like, they're parasites. They steal current from where we don't want it to go. You also get parasitic inductances. Inductive reactance is similar to capacitive reactance, but slightly different. An inductor is basically just a coil of wire. Do I have an inductor to show you? Yes, I do have a jar of inductors. I can get one out for you. Here is an inductor. This is actually a coil multiplication joke, but it is basically an inductor. It is a coil of wire wrapped around a thing. The inductors, because of AC being changing direction, inductors will oppose a change in current. The magnetic field I was talking about will build up in this coil, and it gets stored in the magnetic core of this inductor. And when you try to change that, so when the AC turns around to go back down or whatever, the inductor will fight that and create an opposing force, which is the inductive reactance. So the coils on this might only have a resistance of, say, 1 ohm, but the inductive reactance of this will be much, much higher than 1 ohm. So they will also leak current. The inductive losses are less bad. Inductive and capacitive loads also cause problems with a thing called power factor. So how I mentioned before that there's magic with substations you can do to turn 3-phase into 12. The way that works, I will not go into details because it's extremely complicated. But basically the way that works is an inductive load or a capacitive load will cause a lead or lag in the current draw as opposed to the voltage waveform. Don't worry if you didn't understand a word of what that means, because it doesn't matter, but basically what that means in practice is that the current flowing to the load is more current than the load actually uses. This sounds very, very unlogical, like it doesn't make sense, but just trust me. The way it works is if you have an AC waveform like this, if you have, say, an inductive or capacitive load, the current waveform might look like this, or it might look like this, depending on what the load is. But that leading or lagging, at worst it will be 180 degrees out of phase. That leading or lagging causes the apparent power, which is the actual amps flowing through the cable, to be higher than the amount of current the load actually uses, which is the difference between apparent power and reactive power, and this is getting very deep into very complicated theory I do not want to be explaining because it's complicated as anything. But the simplest way to explain it is basically that's bad, because it means, let's say, for example, I have a monitor which is plugged in behind me for the scope on a power meter, so I can tell you the statistics. It is currently drawing 230 milliamps, and it is using 30 watts. So 230 milliamps, and it uses 30 watts. Let me get a calculator and we can do some maths. 230 milliamps is 0.23 amp. Amps times volts equals power. So we're going to be doing 0.23 times, what is the current mains voltage? It is 242 volts. That's quite low for here, but it must be about dinner time, so that's why. So if we take our calculator, we do 0.23 times 242. That will give equals 55.66. So the monitor is drawing 55.66 volt amp VA. That's the apparent power, because that's how much current is drawing. That's what it apparently uses. In reality, it only actually uses 30 watts. So it is drawing more power from the grid than it actually uses. It doesn't use those additional, whatever that is, 25.6 watts. That power is never used. It's returned to the grid. It's just temporarily stored. But I'm doing a really bad job of explaining how this works. But basically, that additional load, so you are carrying, if we do... so you're carrying like 25.66 watts more power than is actually needed. So we have to rate the transformers in the substation has to be rated for more current. The power pylons have to be rated to carry more amps. Everything has to be bigger to carry this additional power here, which doesn't do anything. It doesn't do anything at all. It flows and then goes back. It never does any work. And with DC, this doesn't happen. With DC, because the power can't be out of phase, you can't have these kind of losses. The power factor of that is 0.53, according to my meter there, which is pretty terrible. Power factor will range from 0 to 1, with 1 being what's known as unity, which is where they're perfectly in phase with each other, and 0 is where they're 180 degrees out of phase. A power factor of 0 is impossible. Well, physically it's impossible because you always will have a capacitance from the cable. You can see an example of cable capacitance actually in part 1, where I showed the IR meter, the insulation resistance meter, and you saw the current bump when I pressed the button. That was from the capacitive effects of the cable charging up and it charging, so it drew more current while it charged the capacitor, and then that went away when the voltage rose up. But these effects of the capacitive draws and the inductive losses and bad power factor loads, all of that combined causes substantial amounts of loss in the cables. If you transmit DC, the only losses you have are corona discharge related losses, which is where the power basically conducts through the air to Earth, and DC resistive losses. You also have the conversion losses for going between AC and DC on each end, but those are fairly minor in comparison to the other stuff. Well, I say they're fairly minor. They're like 90% efficient, usually 90-95% efficient, so that's not much. The DC transmission is much more efficient because of that, but as I said, it was much more complicated to do, and it was only possible very recently, so they accepted these losses of AC transmission because it allowed them to step the voltages up, and that allows them to transmit long distance and make the grid much more efficient and much more reliable. Hopefully this makes sense. I'm really getting into deep weeds of nonsense here, so hopefully this makes sense. Here is a demonstration I thought I would do for you to show capacitive power limiting, or capacitors acting like resistors in AC circuits, limiting power without dissipating heat, or without wasting power as heat. What I have here, this is a 60 watt bulb wired to a bulb holder to my power analyzer. Note, do not try this at home, just don't. I am a trained professional, I know what I'm doing. I know that sounds cheesy, but I actually am. I know what I'm doing, I'm taking precautions. Don't mess with mains at home. But anyway, you will see when I turn the power on to this, the bulb turns on, so I'll shield you from that so you can read the screen. And we are drawing 62 watts, the power factor is 0.997, and it is drawing 250 milliamps. I will now turn this off, and we will put a big beefy capacitor in line with it. I will then attach these dodgy clips in order to put the capacitor in series with the bulb. And when I turn it back on, you can see the bulb is dimmer. If I shield you again, you'll see we're now drawing 220 milliamps, we're only dissipating 44 watts, and the power factor has dropped to 0.8 because the capacitive load now. The thing I would say is I did some calculations about this before we did this. The capacitive reactance of this capacitor, I don't touch it because it's live, but that is 636 ohms, which means this is equivalent to a 636 ohm resistor. However, a 636 ohm resistor would be dissipating 83 watts if we banged it straight across the mains. The actual volt drop across this capacitor would be less, so the actual dissipation from it would be less. I'm not covering that very well, am I? The actual dissipation from it would be less, but still, 83 watts is a lot of power. That's twice as much power as this light bulb is using now. Whereas this capacitor, I can touch it outside, is not even warm. There is no dissipation whatsoever, so you can see in that way it's more efficient. However, the power factor related losses are problematic on the scale of a grid. I'm going to turn this off because that bulb is getting quite hot. But hopefully you could see what I mean about how the capacitor will limit the current without using power. It will limit current like a resistor without actively using it to make heat like a resistor would. This is an even more stupid idea than what I was doing before, so really don't do this at home. But what I've done is I've put a resistive limiter in series now, so I've put about 600 ohms of resistance in series with the bulb. And we'll see what happens when I turn it on. I'm not actually sure what's going to happen. I have a guess at what's going to happen, but I'm not 100% sure, so let's have a look. Ah yes, would you look at that, that is what I was expecting. Those resistors are none too happy. Ooh, sparks. Yes. So, as you can see, that capacitor is clearly far more efficient at not dissipating heat than those poor resistors which just sacrificed themselves for the good of science. Honestly, that's about it. There is a load more that I could get into, but it starts getting really messy and horrible and just so horribly complicated. There's just a couple of things I want to mention about AC before we finish. One is that when people talk about AC voltage, there's a few things I can talk about. There is the RMS voltage, which is root mean squared voltage. That is the DC equivalent voltage. So 230 volt RMS is the same as 230 volt DC when you pass it through a straight resistive load. The 230 volt RMS that comes out of the wall sockets, the actual peak voltage, the maximum voltage, is somewhere closer to 300-ish volts, because it is the RMS voltage times the square root of 2. That will tell you the peak voltage. You can do the peak-to-peak voltage as well, which is the difference between the two peaks. And you can do the average voltage. There's various different ways you can measure AC voltage depending on what you're interested in. The other thing that I wanted to mention was that I talked about all the weird effects you get, like capacitive coupling and inductive coupling and that kind of thing. All of that gets way more pronounced at high frequency. So when you start getting into what's called RF, which is radio frequency territory, things get so messy and it's ridiculous. It gets to the point where you can have a wire like this, and if you're passing an RF signal through the wire, and I bend the wire like that, the signal will then stop coming through the wire, because it will come up here and then reflect off the angle and come back down again, rather than going round. It gets to be so pernickety, and like if you have a 90-degree bend, the RF signal won't go around it. It gets to be a complete mess. RF science is like you could do entire PhDs on the subject, and people, believe me, people have. The whole thing is just a complete disaster. So if you're interested, go look into it yourself, but I am not getting into that here. Other than that, I hope you've enjoyed this video. I hope it's been informative. As usual, any questions, leave them in the comments below and I will do my best to answer them for you. Thank you so much for watching. Like, share, subscribe. I will be putting out more videos like this talking about some basic components in the future, so stay tuned for that. And I will see you in the next one.